So, a good example of concavity to show you that it works, the second derivative tells you about concavity, is go back to x cubed here. F of x equals x cubed. Your first derivative is 3x, then your second derivative is 6x. Now, we already know a lot about x cubed. It looks like that. But as far as concavity, what do you see there? Is this concave up or down? This side. The negative side. Concave down, isn't it? It's bowed like that. And so that's concave down. However, on this side, it's bowed up, isn't it? So it's concave up on this side. And so at 0, we've got a break of concavity. It's concave down on this side, concave up on this side. Well, do you see that the first derivative didn't tell us much about, it didn't give us local max or min, but that's not what we're looking at. Look at the second derivative. Do you see, if I solve that equal to 0, in other words, do a critical number for the second derivative, what does that give me? It gives me x is 0, which that's not coincidence that there's a break of concavity there at x is 0, a change in concavity. All right, but then also look at this. What is the second derivative on this side? What is the second derivative at negative 1? It's negative 6. What's the second derivative at negative 2? It's negative 12. What's the second derivative on this side? Second derivative at 1. It's positive 6. Second derivative at 2. It's 12. Do you see something there? Concave down is when the second derivative is what? When the second derivative is negative, it's concave down. Let's see, how do we want to state this? Yeah. If f prime of x is less than 0, negative, for all x in interval I, then f is concave down for interval I. If f double prime of x is greater than 0, that's concave up for all x and I. Same story. Then f is concave down, concave up, sorry. Okay? And so we're going to do the very same thing for the second derivative. Find the critical numbers. They're not critical numbers of the function, but I guess they're the critical numbers of the derivative. But anyway, find those critical numbers for your second derivative. And then look at signs, positive or negative, for your second derivative. And that'll tell you about concave up or concave down. All right. Okay, use second derivative to find the intervals of concavity. and inflection points. All right, so here's f of x equals negative x to the fourth plus 5x squared plus 6. So that's second derivative, so we got to do the second. We've got our first derivative is negative 4x cubed plus 10x. We're interested in the second derivative. That's negative 12x squared plus 10. So yeah, for the concavity, we do the very same thing. We set it to 0 or look at where it does not exist. In this case, it's just where it's 0. Also look out for f double prime does not exist. That can happen. Concavity changes can happen at those two. Not in this case, though. Just equal to 0. So set that equal to 0. Solve it out. Subtract 10. And we've got x squared equals, what was that, 5/6? So x is either plus or minus the square root of 5/6. Now that doesn't tell me anything about, right now, that we can note, anything about local mins and maxes. It just tells me about concavity. This, we're going to do the same thing, do a little chart here. Break up our graph using those 2 points, which that's not a very big number. It's, was it 0.8 or something? I don't know. Square root of 5/6. Square root of 5/6 is 0.9. Okay. So it's close to ones. All right. So we got negative square root of 5/6 here, positive square root of 5/6 here. For concavity, that's where the graph breaks down. So guess what we do to figure out where it's concave up and concave down? We look at a value in each part. So look at the second derivative in this part, which I could use -1, couldn't I? So plug this into the second derivative. So I'm plugging it in here now. -1, so that'd be negative 12 times positive 1 plus 10. So that'd be negative 12 plus 10. That gives me a -2. What does that tell me? Does it tell me it's decreasing, does it? No, this tells me, since the second derivative is negative, it's concave, which way? Down. Concave down? Yeah, it's good that negative is down, again, concave down. All right, so then do the same thing in here. F double prime is 0. That'd be positive 10, wouldn't it? So the second derivative is positive, so that tells me concave up. And then over here we could do f double prime of 1. That would be the same thing. -2 again, wouldn't it? So f double prime is negative, so that's concave down. Yeah, it is nice. Down and up kind of go the same for the second derivative, so that is pretty nice. Okay, so intervals of concavity do the same thing. Where is it concave up? Well, it's between these two, isn't it? It's between the negative square root of 5/6 and positive square root of 5/6. Where is it concave down? Well, it's concave down negative infinity to negative square root of 5/6. And it's concave down 5/6 to infinity, square root of 5/6. Any inflection points? I do believe I have 2 inflection points, don't I? Now again, these are points, and so we want x comma y format. So what is one inflection point? Well, we have concave down to concave up right here at negative square root of 5, 6. So negative square root of 5, 6, comma, what's the y value? Well, you can figure that out if you want to. The y value would be, plug that in, but I say let's just write f of the square root of negative 5, 6. They may want you to do more with that, but you can if you want. But and then positive square root of 5, 6, let's do the same thing. How's that sound? Save us a little bit of work. Okay, so basically it. So what I'll have you do on the homework is one like this. Any question on that one? Use f prime and f double prime to find A, intervals of increase and decrease. I'll abbreviate quite a bit here. B, the local mans and maxes. And C, the intervals of concavity and inflection points. For this function, f of x equals, let's do 9, excuse me, x to the 4/3 minus 3x. That's a little different one than we've had yet. Okay, well, let's just start with A. Well, A and B kind of go together, don't they? For intervals of increase and local mins and maxes, what are we looking at? That's the first derivative, right? First derivative test. So let's get work here on first derivative. So first derivative, that would be 9 times 4/3 x to the 1/3 minus 3. So we need the critical numbers off of that. Well, let's simplify it. It's 12x to the 1/3 minus 3. I need the critical numbers off that, so what do? Set that equal to 0. What am I going to do with that, though? Well, x to the 1/3 is also known as cube root. Cube root, okay. So let's do this. Let's add 3, divide by 12. So we get x to the 1/3 equals 1/4. And then to solve a cube root equation, we do the same thing as we do a square root equation. Cube both sides. So that'll cancel out. So we get x is equal to 1/64. Okay? So what do we do with that? Well, that tells me about increasing and decreasing, and it tells me about local mins and maxes as well. 1/64, well, that's not very far over here. It's right there. What do I do with that? Well, look on either side. I look at the first derivative, right? Do a value for the first derivative on this side, which good value there would be 0, wouldn't it? Calculate the first derivative of 0. Well, there's the first derivative right there. 12 times 0 to the 1/3 minus 3, what is that going to give you? Well, 0 to the 1/3 is 0. 12 times 0 is it's negative 3, isn't it? So I've got f prime is negative over here. And I'm going to go ahead and, I'm talking first derivative, that's sloping downward. Then on the other side, I could do 1. 12 times 1 to the 1/3 minus 3. Hey, that's going to be 12 times 1 minus 3. That's going to be 9. So f prime is positive on this side, so that means it is headed upward. What does that tell me? Increasing and decreasing is one. There we go. Okay. That tells me there that it is increasing where? From 1/64 to infinity? And it's decreasing from negative infinity to 1/64. What does it also tell me? It also tells me that I have what at 1/64? Well, it's down to up, so that's no, not inflection point yet. Remember, inflection point, that's going to be second derivative. Now that tells me down to up, tells me on first derivative, local min, right? Down, up. So there's a local min. Local min at 1/64, so let's say local min is f of 1/64. Remember, local mins and maxes are y values, function values. Okay? With me on that. So that's all on the first derivative. So that's A and B. That's first derivative stuff. C is second derivative stuff. So let's give me a little more room here. Let's do the second derivative. Second derivative comes off my first derivative, which is here. So it'll be 12 times 1/3 x to the y. Negative 2/3, 1/3 minus 1. And then derivative of that 0, so its second derivative is, that cancels out to 4x to the minus 2/3. All right, so what are we going to do with that? Find the quote-unquote critical numbers, but it's not critical numbers of the function, but in a sense, critical numbers of the derivative. But what do you got there? Well, 4x to the negative 2/3 equals 0. If I set it to 0, what you got? Well, think of it this way. 4x to the negative 2/3 is 4 over x to 2. Is that going to equal 0? Nope. Not going to be equal to 0. You can't solve that. However, that's second derivative equals 0. What else do I need to look at? Second derivative does not exist. Is there a value for that that does not exist? That would be, think of it in this terms. Think of it in terms of, yeah, again, where denominator equals 0, right? So I do get one. I do get a critical number at when would x to the 2/3 equal 0? 0. Okay. So x equals 0 is a critical second derivative. So yeah, the break in concavity is just going to be at 0. Or, yeah. So I need to look at the second derivative on either side of 0. So second derivative of negative 1, whichever one you want to do here, let's do it here since positive exponents are much better than negative exponents. What is 4 over negative 1 to the 2/3? Is that a real number? Yeah. Turns out, what is it? What is 4 over negative 1? Well, again, that's cube root. Cube root of negative 1 is negative 1. But then, what does this mean? Square it? It's going to be positive 1. And you can plug it in your calculator if you want to. But yeah, that's going to be a positive 1. So the second derivative is going to be positive. What does that tell me? Concave up. What about this side? Well, it's a little easier computing. Do the second derivative at positive 1. Well, 1 to anything is 1. So that's also positive 4. Second derivative is positive on this side, so it's concave up as well. Concave up on both sides. So can I just say negative infinity, positive infinity? Nope. At 0, it's neither concave up or down. because at 0 it's undefined. The second derivative is. So what I have to do for concave up here is break it up. Go from negative infinity to 0, and then 0 to infinity. See the difference? That's not quite negative infinity to what's missing. Zero's out, you see. How about that? Oh, inflection point. Do I have a change in concavity? Nope. It's concave up here. It's concave up on this side, so there's no concave change in concavity. All right? Question or concern?